perpendicular bisector theorem of a triangle states that if a point is on the perpendicular bisector of a segment, then it's equidistant from the endpoints of the triangle. For example, in triangle ABC, in the hypothesis, xy has to be perpendicular to AB, ya has to be congruent to yb. In the conclusion, x is equidistant from A and B, and x has to be the equal length to xb. Now let's move on to the converse of the perpendicular bisector theorem. It states that if a point is equidistant from the endpoints of the segment, then it's on the perpendicular bisector of the segment. This theorem is similar to the perpendicular bisector theorem, but with one major difference. It's in the effect of the perpendicular bisector theorem said backwards. The clue is in the name. It's called the converse, which means the switching of the hypothesis and conclusion of a conditional statement. So for example, in triangle ABC, in the hypothesis we can see that xa is equal to xb, and in the conclusion we can see that xy is perpendicular to AB and ya is congruent to yb. The point of concurrency. This is the generic term to explain the intersection of three or more lines at one point. The reason that the term is called the point of concurrency is that the three or more lines that are intersecting at the same point are concurrent. The definition of concurrent lines is of three or more lines meeting at or tending towards one point, meaning the point of concurrency. The point of concurrency for perpendicular bisectors is referred to as the circumcenter of the triangle. Let's have a look at this theorem. The circumcenter of a triangle is equidistant from the vertices of the triangle. So, for example, in triangle ABC, we can assume a point P, which is now the circumcenter. This means it is equidistant from the three vertices, and therefore PA is equal to PB, which is equal to PC. The circumcenter can be inside of the triangle if it's an acute triangle, on the triangle if it's a right triangle, or outside of the triangle if it's an obtuse triangle. The angle bisector theorem states that if a point is on the bisector of an angle, then it's equidistant from the sides of the angle. So, for example, given angle APB, we can take any point along the bisector. Let's call this point point C, and if APC is congruent to BPC, then AC is equal to BC. Now let's move on to the converse of the angle bisector theorem. It states that if the point in the interior of an angle is equidistant from the sides of the angle, then it's on the bisector of the angle. Again, we need to take into account that this theorem is similar to the angle bisector theorem, but with one major difference. It's in the effect of the angle bisector theorem said backwards. The clue is in the name. It's called the converse, which means the switching of the hypothesis and conclusion in a conditional statement. In the same example, we can now just simply switch around the hypothesis and conclusion of the conditional statement formatted as the theorem. The conditional statement is the formatted theorem, and say that AC is equal to BC. In this hypothesis, and then say in the conclusion that angle ABC is congruent to angle BPC. A triangle has three interior angles, so it has three angle bisectors. The angle bisectors of a triangle are also concurrent. This point of concurrency is referred to as the incenter of the triangle. Let's have a look at its theorem. The theorem states that the incenter of a triangle is equidistant from the sides of the triangle. In this triangle ABC, there are three angle bisectors drawn, and that all of them meet at the incenter of the triangle. We can clearly see that these are the angle bisectors, as we can see that the segment bisectors are splitting each interior angle of the triangle into two congruent angles. And let's call the incenter point P. We also have to name the points where the three closest segments to the triangle sides are perpendicular to a 90-degree angle, also seen as earlier. So let's name these points Y, X, and Z. As stated in the incenter theorem, all of the segments are the same distance to the sides of the triangle, and this means that the three segments PY, PX, and PZ are all congruent to each other. A median of a triangle is a segment whose endpoints are a vertex of the triangle and a midpoint of the opposite side. In this triangle ABC, we can clearly see the midpoint because it goes through one vertex of the triangle to the other vertex of the triangle, the midpoint of the opposite-sided segment. Let's call that midpoint D. Therefore, AD and DB are congruent as the midpoint has divided the side into two congruent segments. A triangle has three medians. Those medians of a triangle are concurrent, and this point of concurrency is referred to as the centroid of the triangle. Let's have a look at its theorem. The theorem states the centroid of the triangle is located 2/3 of the distance from each vertex to the midpoint of the opposite side. In this triangle ABC, there are three medians drawn that all meet at the centroid of the triangle. They all have endpoints, with one being the vertex of the triangle and the other endpoint being the midpoint of the opposite side, dividing the opposite sides of the vertex of the triangle into two congruent segments. Let's now call the centroid of the triangle point P. The median with an endpoint B, median BZ. The median with an endpoint Z, median ZX, and the median with an endpoint A, median AY. The theorem meant when it stated 2/3 distance was to how the proportion of the median that has endpoints, including a vertex of the triangle and the centroid, are the larger portions of the overall length of the median. This longer portion of the median is equal to 2/3 of the length of the entire median. The longer portion is also known as double the length of the smaller portion of the median. An altitude of a triangle is a line segment through a vertex and a perpendicular to, i.e. forming a right angle with, a line containing the base, the segment opposite the vertex. The length of the altitude, often simply called the altitude, is the distance between the base and the vertex, which could be extended. A triangle has three altitudes. Those altitudes of a triangle are concurrent, and this point of concurrency is referred to as the orthocenter of the triangle. Let's have a look at what an orthocenter is. The orthocenter is the point where all three altitudes of the triangle intersect. The orthocenter of a triangle can either occur in the triangle, acute triangle, on the triangle, which is a right triangle, or outside of the triangle, obtuse triangle. This will be shown in the following examples. So, as we can see here in triangles ABC, the altitudes are AD, BE, and CF. These altitudes intersect in the acute triangle. They intersect on the right triangle, as we can see, and they intersect outside the obtuse triangle in this image presented here. A midsegment of a triangle is a line segment of a triangle that joins the midpoints of a triangle. Every triangle has three midsegments. Those three segments form the midsegment triangle. The midsegments either side of the midpoint are equal to one another. Let's have a look at the triangle midsegment theorem. Any midsegment of a triangle is parallel to the side of the triangle and it's half the side's length. One of the midsegments in the triangle is parallel to one of the sides in the triangle. This being parallel is represented by the parallel tick marks, and the midsegment being half of the length of the triangle side is represented by the 1x versus 2x, as 2x is double the distance, to 1x. If we apply these ideas to an entire midsegment drawn out triangle, we can see that the corresponding parallel sides are always double the length to the corresponding midsegment. As always, thanks so much for watching this video. I really hope you enjoyed it, and if you did, please remember to leave a like down below and to subscribe to my How to Master channel. This would help me in widening this channel and creating more videos like this in the future. Please also leave a comment down below if you have any concerns or suggestions for more how-to videos like this in the future.